I'm the founding member and the current vice president of the club.
So, thank you all for coming. It's very good to see everybody here. So today is about talking about our journey to Mars. But why do we want to go to Mars anyway? There are many reasons. Some of them could be that, being human, it's our innate nature to want to explore, to travel, understand our place in the universe. Some of this exploration can even maybe help us understand where Earth might end up in the future, like Mars, maybe. Or it can even help us protect our species against extinction one day. So lots of good reasons for us to go to Mars. So today's about our journey onward to Mars. What does that really mean? So today, NASA is talking a lot about the Lunar Gateway and all the waypoints to go to the Red Planet. They're also collaborating with many international space agencies, and there's a lot of private companies involved. So in all of this, where does academia, and Purdue especially, fit into the whole picture? So that's what we're here to find out today. Learn about what are the different efforts that's happening on campus that's contributing to these space endeavors, and how everybody here, if you would like to, become more involved in these pursuits to help improve space exploration efforts. So that's why we're here today. And next slide. So I'd like to invite our Mars Society members to the front super quick, if you can. Some of us are missing today, but some of us should be hiding up the back. I guess, John, Paul, come down. Someone? Okay, some of them are still working at the back. I just wanted to say that we have a very strong team of great mentors with our faculty, and a lot of great and hardworking undergrads and grad students here who've worked very hard to put this event together, to publicize it, to promote it, and make sure everything goes smoothly today. So if we could just give it up for them, please. So I'll pass it over to Shitich for a second.
So today I will be going to talk about what all events we have done so far. So we started as a small organization. We are only 1.5 years old. And the reason for starting this is that I came to know about a competition long back in 2013-14. And I was very lucky to know about that competition. And when we participated, Purdue went there, and most of the faculty advisors are sitting here. Under their guidance and the talent here, when we went out and competed against 38 teams across the world, we secured first spot. So that is what it means to be at Purdue. It's like world-class education, and we wanted to see what happens when we take this education out to the real world and compete against others. So that's how, some of us went there, we got first prize, but then it was almost like, okay, nothing is happening. But we wanted these opportunities to be known to other people as well. So we started doing that, and for that very reason, we started this organization, so that we make people aware about, a lot of missions are going in different parts of the world related to Mars, or related to space in general, related to human settlement. So we wanted to let people know about that. Also, we think that, Mars or some other place is our next destination. Humans are going to explore no matter what, because it's inside us. We are not going to stop. We will explore. So we want the next generation to be keen and to know about all these things as well, and to be inspired about this. So we do several outreach events at different elementary schools out here. We have done 2 events in the past, and they have been very successful. We have around 100 participants each time. So one was that. When we started this organization, another vision we had is that there is a place called Mars Desert Research Station. And there are a lot of teams around the world, including professionals, not just universities, who participate in this. And it's very competitive. Not every team gets in. But Purdue as a team has never gone there in its history. 3 students have gone individually, but never as a team. So we found this organization as an excuse to bring all set of people from different departments and form a formidable team. And then we presented our research proposals. And as expected, we were selected in top 14 teams in the world. And we are going this December, 7 of the students. So that's incredible. Like every time we participate, we get some prize or we get selected in something. So that is again and again showing that there is like high quality education that is being provided here. And after that, what we observed is that only 7 students out of 40,000 students got a chance to go to that place. And it takes a lot of money, effort, time, everything to go to that place. So we met an organization who is actually trying to provide analog astronautics. And analog astronautics, I mean that we are not actually going to Mars, but we are going in a simulated place which is like Mars. And we do things as if we are on Mars, Martian astronaut. So we wanted everyone to have taste of it, irrespective of the department. And then we carried out a survey. You won't believe people from English department said they want to do analog astronautics. So that is what we thought, and that is what is happening. People want to do this. We don't want anyone to leave out. So we started this organization to provide all such opportunities. And in April, we are going to have a festival related to Mars, in which most of you will be donning space suits and doing missions as if you are on Mars. So we are going to do that. So this forum is just, one big start, kickstart to our organization. And then there are lots of our awesome advisors, faculty advisors, who are going to give wonderful talks today. So let's hear more from them. And I will pass on the mic back to Ash.
So just very quickly, next slide. So Shita spoke to you about some of the events we've done, and today is about our journey to Mars. So just for a second, if we can imagine, we're taking a holiday to California. When we were planning this trip, we're thinking, oh, should we go by plane, by car, by train? What do we pack? How much do we pack? How do we entertain ourselves along the way? And when we get there, what do we explore? How do we have fun over there? And what restaurant do we want to go to? Or do I stay in an Airbnb or a hotel? There's so many questions. Similarly, when we plan our journey to Mars, we're asking essentially the same questions, but we have a lot of different types of options available. So, it's a whole team, it's a whole industry that it takes to answer such questions. And today we have an amazing group of faculty here who's going to talk to us about how their research and work are contributing to such efforts. And it's going to be very exciting, and I hope we all take something away from this today. So without further ado,
Okay, so first we are going to invite someone very special. And we are trying to keep it interesting, so we are going to rhyme it. So this other person, this professor, amazing professor, is a PhD from Cornell.
My bad.
Sorry about the English issues, always we have some English issues, but this professor is a PhD from Cornell who loves terrestrial exploration. Geology and remote sensing are her vocation. Investigating life on Mars is her current application. Let's welcome from EAPS, Professor Hogan. So Professor Hogan also happens to be the advisor for our MDRS team, the analog astronaut team that is going to Mars Research Station. So just giving a fact.
All right, great. Yeah, so I'm Bryony Bergen from Planetary Sciences Group over in Hampton. So today I'll be talking about what we know is it might actually happen on Mars in the next 10 years or so. Of course, human exploration of Mars, we're still trying to figure out when that's going to happen and how. And NASA does have plans to do more on Mars in the next 10 years. So today, just briefly, I'll be talking about the Mars 2020 rover and Mars sample return and NASA's plan for robotic exploration in the next 10 years or so. So the background for this is, right now we're coming sort of to the end of the modern Mars exploration program. And so this is in terms of thinking about the science of Mars and how to explore the geology of Mars, the history of Mars. And so for NASA, this is all built around a very specific sequence of investigations. Of course, our big goal for Mars in terms of science is looking for signs of life outside of the Earth. And right now, as far as we know, Mars is our best place to do that. It's the best opportunity we have to find signs of life beyond Earth, because we know in the past Mars was once very Earth-like. It had rivers, lakes, maybe it had oceans, it had rain. So we know it's, because of that, we're very optimistic that Mars may have once hosted life. And so to look for this, to try to understand where we can go on Mars to look for life, NASA has followed a very specific series of steps over the last 15 years or so. And that's basically through these 3 steps. So first, follow the water. This was the Spirit and Opportunity rovers that went to Meridiani and Planum and Gusev Crater. They were sent there to confirm that Mars was in fact once Earth-like, that it had liquid water flowing on the surface. The second step was to find a habitable environment. So this liquid water, was it there, and also were the environments it was present in actually conducive to life living in them? So did they have the chemistry and all those other things that life needs to survive? Finally, the next step is, once you know where the habitable environments were on ancient Mars, then you can actually go and look for signs of the life that once existed. And so these 3 steps correspond to 3 generations of rover, as I started to mention. So the Spirit and Opportunity rovers, you can see on the left side over here, those are basically robotic geologists sent to Mars to look for, to follow the water, to look for signs of ancient aqueous environments on Mars. Of course, following that, we have the Curiosity rover shown on the right. This is a big beast of a rover that is currently on Mars today, and that's looking for these ancient habitable environments. And of course, down here in the bottom left, you can see the Sojourner rover, which went to Mars in the 90s with Mars Pathfinder, and was sort of a precursor to this modern era of robotic exploration. The rovers, you can see here, they're shown in the Mars Yard at JPL, where we test the mobility systems on the rovers. So just to start, I can't talk about rovers without mentioning anyway. So we're seeking out these ancient habitable environments in Gale craters. This is a really big crater on Mars that has this huge mound of layered sediments in the middle. This mound is over 5 kilometers high, so it's as high as the Grand Canyon is deep. So the Curiosity rover landed right about here. Right about here, sort of in this part of the crater, and we're climbing this mountain called Mount Sharp. So this is the map the Curiosity's fallen. In the last 5 years, we've traversed over 15 kilometers on the surface of Mars with this giant rover. And today we've actually just reached a major milestone in the past month or so.
Oh gosh. So this is
Thanks. Reached a major milestone with the rover right about here. We're climbing up the mountain in this direction. We've reached the hematite unit, which is this big ridge that circles the side of the mountain. And so now we have these fantastic views looking off of the ridge. So this was just from taken 2 weeks ago on Mars. So here you can see we're looking off the mountain into the distance. We're actually looking at the rim of Gale crater here. And so this looks like a mountain chain, but on Mars, the only mountain chains you really get are the rims of impact craters. So they're always circular. It's just a beautiful image. It's one of my favorites of the mission so far. So that's where we are on Mars today. So that's the Curiosity rover. Again, it's looking for these ancient habitable environments. We found tons of evidence for basically everything you're looking at here are ancient lake deposits. This whole crater was once filled with a series of lakes that lasted at least millions of years. And that's what we found so far. There's more to come. But of course, the next rover that's following on this is the Mars 2020 rover. So this is really the first big Mars mission for NASA in the coming decade. And so the Mars 2020 rover is going to build on these previous generations of robotic missions by searching for biosignatures on Mars, by actually going to Mars to search for specific signs of ancient life. And also, in that process, collect samples that we'll bring back through Mars Sample Return, which has been a huge goal of the Mars community ever since the 1970s. Okay, so what is a biosignature? A biosignature is basically a sign of life in the rock record. We look for these things on Earth as well to try to understand the ancient history of life on Earth. Now we want to do it on Mars. This includes things like organics, microfossils, big fossils, chemistry, isotopes. So we can look for some of these with our rover, but a lot of them are really difficult to do with a robotic package. And so we'll have to bring rocks back to Earth as well to look for some of these more detailed things. You know, things like isotopes are really hard to do on a planetary surface. So Mars 2020 itself is going to look a lot like the Curiosity rover, but it'll have a completely different suite of instruments. In particular, we'll have some new instruments that can actually detect organic molecules through remote sensing using things like Raman spectroscopy, which is great detecting organics. We'll also have a radar system on board to look for subsurface water or ice, as well as other things like the cameras. I'm also a co-investigator on Mars 2020 rover on the camera system. And so we're really excited about all these new technologies we're studying on Mars. So the strategy here, so like I said, one of the big things with 2020 is we're going to go look for signs of life on Mars, but ultimately, the only way we'll be able to confirm whether or not we found biosignatures is by bringing those rocks back to Earth to look at labs and our much better, more improved labs back here on Earth. And so Mars 2020 will be the first step towards Mars sample return. And so while we're evaluating these rocks for biosignatures, we'll also be taking samples. You can see the approximate size of a sample from Mars 2020 here. It's about the size of a pencil, number 2 pencil. So not a lot of rock, but hopefully it's enough. So Mars 2020 will collect about 20 to 30 samples on the surface, and then it'll leave them behind at cache depots for a future rover to come collect to start the process of Mars sample return. So Mars sample return is incredibly difficult. It's always been hard. That's why we've wanted it for over 50 years now, but it hasn't happened. And it's partly because it requires so many steps. So we have Mars 2020, which is down here collecting and caching the samples. You have to send another rover to fetch those samples and collect them in one place, and to bring them to an ascent vehicle. So here's shown as a Mars ascent vehicle. Now, of course, we've never done this, or we've never launched a rocket up on other planets. This is an entirely new type of technology. Eventually, then that Mars ascent vehicle with its little, kind of head size that cache the samples will get into orbit. It will rendezvous with some sort of orbital asset that will then bring those samples back to Earth. So you can start to see how hard all of this is, right? Every step of this is incredibly challenging, and it's a whole NASA flagship mission like Curiosity really on its own. That's why we haven't done it yet. But we're really hopeful that now we know enough about Mars that we can really justify that series of missions. Okay, so right now on the science team that I'm part of, we're really spending a lot of our time doing is trying to figure out where we go. This might be our only shot to ever get samples back from Mars. So what one place do you go to on an entire planet to pick samples for your only samples from that planet? If you had to go one place on Earth to understand the entire history of Earth, where would you go? Right? It's a really hard question. So we're trying to work that out. We have a bunch of different opportunities we're looking into, different landing sites. We're down to 3 primary landing sites, which you can ask about later if you're interested. So really the point of this is that Mars sample return, NASA, even human exploration, is very invested in this idea because it's a key step toward human exploration of Mars. There are a lot of people who think we should not go to Mars until we have a well-characterized sample of Mars back here on Earth, so we know more about the hazards for humans. A lot of the technology I mentioned, things like the Mars ascent vehicle and all of that, is directly related to getting humans on and off Mars as well. And so it's a really great step toward human exploration of Mars that NASA is very involved in. And of course, there'll be more robotic exploration of Mars as we approach humans actually landing on the surface, rovers to characterize landing sites, resources, all these different ideas. So anyway, that's all I have for you guys today, and I'd be happy to take questions now or after later. Thank you.
Thank you so much.
Science is hard, and it's a great motivator for all our missions, so thank you very much. So as for our next speaker, we have, are you ready to do it? Okay. A PhD from Stanford, chatting Wait, even now. Okay, so a PhD from Stanford charting courses among the stars. She directs spacecraft paths like touring cars. Today, she'll illuminate the waypoints to Mars. Let's welcome from AAE, Professor Kathleen Howell, and my advisor.
Okay, I am from Aero and Astro, so I'm on the engineering side of the house. And when you think about going to Mars, there's a parallel development that has to happen. So from our perspective, the question is, how are we going to get there? But we actually have a bigger goal in general because we not only want to say, how are we going to get there, but how are we going to stay there? And so this is a parallel development that's more about long-term. We don't just want to go there and come back, but how do we actually push outward and create a environment, I guess, as well as capabilities that will eventually end up at Mars, but may take some other things along the way. So in that effort, in last March, actually the end of March, it was like March 28th, NASA actually came up with a slightly altered plan that will eventually end up at Mars. But it was all about building up a capability that we're going to be able to use a lot of things for. and that will sort of move human civilization outward, and so that we can more permanently remain in space. And so some of the key elements of that slight shift in direction, was a goal to expand the human presence, of course, beyond LEO, beyond low Earth orbit, and move it out. Actually, the first step will be to move it out closer to the moon. So the feeling was that you needed to have technology that was going to be ready to support near-term missions, and that would mean both human as well as robotic-type missions, but at the same time it would build up capabilities that you could use in the future. So they talked about developing within the Earth, within the moon's orbital radius, an evolvable infrastructure. So in other words, what kind of capabilities do you need to have so that you could eventually build towards Mars? So it's more of a gradual expansion outward. As part of this discussion, there are academic, commercial partners, as well as international. And that's a challenge because not everybody wants the same speed of development, not everyone wants to go to the same places all the time. But this was a shift that was made last spring. This is the new roadmap, so to speak, on how they're going to build things up so that eventually they will end up at Mars. So right now we're in phase 0. And that's just using everything we do have in LEO, understand a lot more, use the space station in order to do some experiments that will set us on the next stage. So I work a lot in phase 1 and 2, which has to do with conducting missions in cislunar space, which means capabilities within lunar orbit. So the goal is to, first of all, starting very quickly, to try to conduct some additional missions in cislunar space and start to assemble the deep space gateway and the transport. So the gateway is really going to be some space facility, sort of taking the space station and moving it out closer to the moon so that it can support activity that will also go translunar. And the deep space transport is a vehicle that's further out, which would actually be setting the stage to go for destinations such as Mars. Now, these buildups are supposed to happen in the 2020s, and then when you get to the 2030s, they would expect to complete the deep space gateway, both as far as its capabilities are concerned, as well as some of the actual additional constructions, and then conduct a simulated Mars mission at that time. So those further out phases are not completely planned, but that's the current roadmap, so to speak. So the Deep Space Gateway is what's occurring currently, and this is to build up the infrastructure within the lunar orbit in order to make the capability possible. So the Deep Space Gateway is going to be out somewhere near the moon, but it's supposed to be sort of a habitat that can last for multiple decades. So they want to place it out there, and eventually it will have some human crew, but it's going to be essentially, or the plan is for it to be like a transportation node. So from Earth you would go up to the gateway, and then you could move to other destinations. It's supposed to support both the human developments as well as robotic type missions. And as a transportation node, working with the commercial partners as well as the international partners, but the goal is that they need to have access to the lunar surface. That's very important to the international partners. But there also needs to be capabilities to move throughout cislunar space, to move to lots of other destinations, and use it as a staging point. Now, it's not clear necessarily that they will put this in a particular orbit and it will stay there. So it has to be able to move around as well as make an assessment. For example, wherever they want to put that particular structure so that it has access to the lunar surface does not necessarily mean that that's the best place to take off to go to Mars in the future. So they need to have some understanding of what all the possibilities are within the lunar radius or the lunar vicinity so that you can move around to support different destinations. So what we're really looking at in my area, and Ash is part of it, we're really looking at what the orbital options are within this environment that we can use to support many different goals and to try to understand what the best locations might be, and if we can actually accomplish it. So right now, with international participation to support the human program, they're looking at staging orbits in the vicinity of the moon. So in this particular case, I wonder which one of these works.
Oh, it's not on.
Okay, never mind. Okay, so these are the I guess, the last set of orbits that they were looking at in order to put the deep space gateway. And this does change and so on, but there's a number of different orbits in the vicinity of the moon, and there's some further out. So when I look at the moon itself, these guys that are in green here actually show lunar orbits that were considered as possible locations for this gateway. Essentially, a space station that's much further away than low Earth orbit. So these are the orbits that were put, for example, very close to the moon, but they are very close to the moon. And that does not necessarily support some of the other goals of being able to leave this orbit and go to Mars, or be able to leave this orbit and go to other destinations. So they also looked at some of these other orbits which are a little further away. In particular, I guess the last ones that were being considered were all orbits that are further out, which means that they have a more complicated dynamical structure, and part of our job is to assess them. So if I look at these a little closer, what I see is that blue one is called a distant retrograde orbit. That's one possibility. The red one is a halo orbit. That's another possibility. Some people think that that's the right orbit to leave to go to Mars. And then the rectilinear halo orbit, which is the one in the black. Now, one of the things about these is that they're also in different planes and so on. So that blue one is in the Earth-Moon plane, pretty much. And those other ones are very much out of plane. So, for example, you see that NRHO down there, which has a very large out-of-plane component below the South Pole, that has attractive characteristics for other reasons. And that red one is speculated that maybe that's an option for what you would want to use for some other transportation. So thinking about all these things is what we do in order to support that characteristic. Now, Earth Exploration Mission 1 is the one that's supposed to launch pretty soon, 2019 probably. And this is the one that's going to go out there and sort of test drive some of these things. So this is one that's going to go out, and it won't have a crew on it, but it will be testing some scenarios in order to go out to one of those larger orbits that's not very close to the moon. It'll spend some time in a DRO and then return to Earth. It's also testing out the SLS system for launch capabilities. This is the one that's going to test out some of those options. This is a little bit simpler image of exactly what this particular mission is going to do. So as far as Exploration Mission EM1 is concerned, it's mostly a test out to see that we can do these kinds of missions, and in preparation for a crewed mission, which will be EM2. Now the crewed mission for EM2 will take a crew out into this vicinity, move them into one of those orbits, in this case the distant retrograde orbit, and then bring the crew back. But this mission is also going to do a couple of other things that are important. So one of them is that it's also going to send out, the crew is going to the distant retrograde orbit, but they're sending out another unit, which is a propulsion unit, that they want to put in what they believe will be the destination orbit for the facility. So as of right now, that's the near rectilinear halo orbit, and so they're going to put a propulsion unit in that orbit that in later EM missions, they would actually rendezvous with. So that's the current plan, and that's what they're going to do in order to set up this expansion. So they are going to put the crew in the blue orbit and then bring them back, and they're going to put the propulsion unit, as of right now, into that black one. So that's what they're talking about right now, with the goal that they want this facility to be something that they can use long term. Now, once they get into EM3 or 4, and they actually put a crew into one of these, right now it's set to be the black one there, they would also use that, for example, Dr. Horgan was talking about sample return missions. They're also considering that this facility may be the one that they bring the sample back to before they send it back to Earth. So this facility should have a lot of lot of capabilities from the trajectory design perspective, and so that's what our job is. This is the red ones are what some of these orbits look like in this particular vicinity. These are the ones that they're looking at as the possibility to set the stage for the deep space gateway. So that's what they're talking about right now. The blue orbits, and it happens to be green in this particular case, but they also want to move back and forth between these two orbits. So that's the kind of thing that we do, is we try to support those capabilities. So that means calculating the orbits. It also means looking at the transfers and so on. Now, one of the other things I said, oh, this is the transfer out, that's the current design to put a crew into the black orbit, which would be in EM3, would be this first opportunity to do that. But there's a lot of other things that happen in this space, and there's a lot of other opportunities to try and understand what all the options are. Which is the best one to get to Mars? How are we actually going to make that happen? How can we actually affect it? So there's lots of other options going forward, and what we do, it's our job to look at a lot of these other options and sort of see what we might be able to accomplish. So that's actually what we do. Our goal is to develop this roadmap within the Earth-Moon space that can then be leveraged in order to go translunar and eventually get us to Mars, but in a way that we have an orbital capability as well as a hardware capability that we can last for many decades. That's it.
Thank you very much. Thank you, Professor Hall, for a wonderful talk and telling us that Moon and missions to International Space Station are also very critical and so important. So, introducing our next speaker. He is a PhD from Georgia Tech, a boilermaker at heart. He is giving hands-on space missions another kickstart, discussing what sets Mars small-sat missions apart. Let's welcome from AE, Professor Spencer.
All right, good evening. There's a revolution going on right now in terms of small satellites. I was actually reading today that a company called Planet has a constellation of small satellites that is imaging every square foot of the Earth on a daily basis. They're downlinking more than a terabyte of data every day. Imagine the big data science that's going to be unleashed by that technology. Okay, next slide. Just to give some context, I spent many years at JPL and worked on missions, both Earth science missions, Topex Poseidon, which had a launch mass of about 2,300 kilograms, as well as planetary missions, this whole slew of missions that were all in the 600 to 900 kilogram range. Also, all of them cost on the order of $400 million. Consider on the order of half $500 million. Okay, then I came to academia, started working with small satellites. LifeSail 1, 5 kilogram spacecraft. Prox 1, 70 kilograms. LifeSail 2, 5 kilograms as well. The LightSail program in total costs about $6 million by comparison. Okay, much smaller missions, much more focused in their scope. LifeSail was a technology demonstration mission, not a space science mission. Here at Purdue, we've also got the aerodynamic deorbit experiment, which is a 1 kilogram, 2 kilogram CubeSat. Okay, so the size of spacecraft have come down dramatically. With those, the cost has come down dramatically as well. What's exciting about small sats is they can target niche areas, space science, that the primary missions, if you're spending $500 million, you may not want to focus those primary missions on these more narrow science goals, but they can still address very important science and technology and infrastructure needs. So today I'm going to talk about some opportunities and some challenges associated with doing these small satellites in the university environment. Now, as I mentioned, there are actually thousands of small sats that have been launched in the last decade, and the rate of launch of these CubeSats and small sats is just accelerating, but all of them have been Earth orbiting so far. The first CubeSats that are actually going to be interplanetary are likely to be the Marco CubeSats, which are going to be launched along with the InSight spacecraft to Mars in May of next year. Okay, and these are two 6-unit CubeSats, literally about this size. whole purpose in life is to fly, fly along behind InSight, and once InSight gets to Mars and starts doing its entry, descent, and landing, you guys might have seen the 7 Minutes of Terror video from Mars, from JPL for previous Mars missions. That 7 Minutes of Terror is very important, okay? And we want to get data back to Earth from that in as close to real time as possible. And InSight is planning on communicating with Mars orbiters as it's entering Mars, but the Marco CubeSats are going to be able to be in position and bin pipe that data back to Earth in near real time. So they have UHF communications from InSight. They have direct-to-Earth X-band communication to Earth. They're using commercial off-the-shelf parts. They're fairly low cost, and this is managed and built by JPL. But importantly, it's built, to JPL standards. Class D, which is their lowest level of, quality control, so to speak, but still done by professional engineers at a very high level. Okay, so what opportunities are coming for university small sats? Well, one particularly interesting opportunity is actually going to be coming up for the second time next year, and it's called Simplex, Small Innovative Missions for Planetary Exploration, funded by NASA, the Science Mission Directorate. The first Simplex opportunity was several years ago. Arizona State University was selected for that, and they're developing a spacecraft that's going to map out hydrogen distribution on the moon. It's called Luna HMAP, selected to fly on EM1, which Professor Howell was talking about. The funding level for that mission was about $5.7 million. So this is a lunar mission for on the order of $6 million. Other opportunities, well, by the way, this next Simplex opportunity, we don't know what the funding level for that's going to be. We hope that it will be large enough that it will enable missions beyond the moon, maybe Mars missions. We're hoping that it will be as high as $100 million. I don't really think it will be, but it could be. Okay? So we'll have to wait and see what that is. Another opportunity is ride-along payload with primary missions. Okay, there's a mission planned called Europa Clipper that's going to Europa in the early 2020s. They put out a concept study, funded a number of different universities and research institutes for potential CubeSat ride-along missions that would ride along with the Europa Clipper spacecraft to the vicinity of Europa, be dropped off, and then do its mission in the Jupiter environment. I would note that Mars 2020 has excess launch mass capability. This has been discussed as potentially being used for CubeSat payloads. It's unlikely that's going to happen. Project managers generally don't like to have, things coming off of their spacecraft, right? But the Marco concept of having being deployed from the launch system and effectively being independent from the primary payload is very interesting as well. Also, other opportunities, privately funded missions, things like crowdsourcing. With a very small Kickstarter campaign, the Planetary Society raised almost $2 million to fund LightSail. That goes a long way towards building and operating a CubeSat. RPM, rich people's money, right? Jeff Bezos spends $1 billion a year, which is kind of throwaway money from Amazon, right? He literally says, this is my pet project, my little company, Blue Origin, which is building launch vehicles. They want to build up capability to go to the moon and perhaps beyond. And that's, RPM, that's kind of throwaway money from Jeff Bezos. Elon Musk, very similar story. So, our economic environment is